So, today we will discuss few problems on continuity, differentiability and application of the derivatives like a mean value theorem, monotonically increasing and decreasing function, so on. But prior to start with the problems, we will take up the topic which we have not covered in the last lecture, that is the Taylor's theorem. So, before that we will first complete that proof of the Taylor's theorem, and statement we have already discussed, but still we rewrite again. This Taylor's theorem is also known as the generalized mean value theorem, and this says if a function f and its derivative up to say order n plus 1 or up to n minus 1 are continuous, up to order n minus 1 are continuous, up to say order n, let us we take up to order n plus 1 are continuous, and continuous over the closed interval, say a to a plus h, okay, this closed interval a b, and differentiable and its derivative and its nth derivative that is f n x. So, here f n x nth derivative exists in the open interval a to a plus h, then there exists at least one number theta lying between 0 and 1, such that the expansion of this function at the point a plus h can be written in the form of a series f a plus h f prime a plus h square over factorial to f double dash a plus h n minus 1 over factorial n minus 1 f of n minus 1 a plus h n over factorial n f n a plus theta h, this expression. So, a function f can be expanded in the power of h, in this form, and the last term is called the remainder. Basically, it is called the Lagrange's form of the remainder. This is called the Lagrange's form of the remainder. There are various forms, we are not interested in the other, just log. Now, here last time we have also, in the last lecture we have taken in a similar statement, because it coincides with the previous. If I choose another form, or we can say of this statement is, if suppose I take f a plus h and let x be a point of the interval a to a plus h, okay, a to h, and let f satisfy the conditions of Taylor's theorem as defined above. As defined above. In the interval a to a plus h, a to a plus h, okay. So that it satisfy the condition for a to x also. Okay. Then if I take a plus x, then the equation 1 can be rewritten in this form. Then equation 1 can be written as f of x equal to f a plus x minus a f prime a plus x minus a whole square over factorial 2 f double dash a plus so on up to say x minus a to the power n minus 1 factorial n minus 1 f n minus a n minus 1 derivative at the point a plus the remainder term r n x, where r n x is as x minus a to the power n divided by factorial n, n derivative at a point a plus theta x minus a, where the theta lying between 0 and 1. Then one can be written in the form this, where h is taking to be as x minus a. So, if in this form, if I take h to be x minus a, then the function is well defined. Function is throughout continuous. Its derivative up to order n minus 1 is continuous over the closed interval a b, and f n plus 1 f n exist. It means they are also differentiable over the open interval a b. When we say f n exists, means the derivative up to order n exists in the open interval a to a plus h, and they are also continuous over the closed interval a to a plus h. Then what he says is, if we picked up any point in the interval a b, so I am taking the point like a corner point x plus h. In fact, this will be a b interval, where I choose a point x in between a b, and that point is a plus h. Then expansion of the function f x in the powers of x minus a, ascending powers of x minus a, can be expressed in this form, where the first n terms is the series and the last term, the nth plus 1th term, that is equal to nth term, is the remainder term, and which called the Lagrange's form of the remainder. And this point is obviously a point, clearly the point a plus theta x minus a. Since theta lying between 0 and 1, so obviously this point belongs to the interval a to x, because it cannot be a, because theta is not 0. It cannot be x, as theta is not 1. Okay, so it lies in between this. So there is some point in between the interval where the remainder term can be expressed. Okay, the proof of this, which we have not done it last time. Let us see the proof. Its proof is simple. In fact, what we do is we construct a function such that so that we can apply the Rolle's theorem, and once you apply the Rolle's theorem, a point c can be obtained where the derivative becomes 0, and from here the remainder term will come. Okay, so that is our idea of the proof. So, let us consider the function phi x as f x plus consider function phi f x plus a plus h minus x f prime x plus a plus x minus x whole square y factorial 2 f double dash x and so on, plus a plus h minus x to the power n minus 1 factorial n minus 1 f n minus 1 x plus a plus h minus x power n, where a is a constant, where A is a constant to be determined such that the value at the end point of phi, that is phi a is equal to phi a plus h. We put the restriction on phi in such a way so that a can be computed. So, suppose I put this restriction and then from here let it be 2. In the 2, if I replace x equal to a and x equal to a plus h, what we get? As soon as you substitute x equal to a plus h, all the terms gets cancelled except you are getting f a plus h. So, we get f of a plus h, and when you take x equal to a, then what you get in the right hand side, we get f a plus h f prime a plus h square by factorial to f double dash a and so on, h to the power n minus 1 factorial n minus 1 f n minus 1 a plus a into h to the power n. Okay. So, this function. Now, the function phi is a continuous function. Since the function phi is continuous over the interval a to a plus h and differentiable in the open interval a to a plus h, and also satisfy the condition phi of a equal to phi of a plus h. Why? If you look the function phi is basically is a linear expression, is an expression which involves the function f x and the term a like L minus x or L minus x square and so on. So, instead of the one x to the power n and the derivative, since function f x and its derivative of 2 orders a n minus 1, they are continuous, and this x to the power n type a alpha x plus beta x to the power n type, they are continuous function. So, product of each term will be continuous. So, phi will be continuous. Similarly, phi is also differentiable, and at the end point of the interval a and a plus h, it attains the value same value. So, we can apply the Rolle's theorem. So, by Rolle's theorem, there exists a point C. So, there exists some theta, there exists theta lying between 0 and 1 such that the derivative of the function at some point a plus theta h is 0. So, a plus theta is a point lying between a to a plus h. Okay. But what is the phi prime x? What phi prime x, if we just go and differentiate it, you will get many terms get cancelled, and only you are getting differentiation of this one term when its derivative is here and this, and rest is telegraphically it gets cancelled. So, we get finally the value is a plus x minus x, a plus h minus x to the power n minus 1 factorial n minus 1 f n x minus p in minus n a plus h minus x to the power n minus 1. This you get. Now, this quantity at x equal to a plus theta h, the phi dash of this number is 0. So, from here what we get? We get h to the power n minus 1 minus theta n minus 1 over factorial n minus 1. Just substitute this value x equal to this number into f n a plus theta h minus p n a 1 minus theta n minus 1 h to the power n minus 1. So, if we solve it, we get the value of a will come out to be the thing that is 1 by factorial n f n a plus theta h, where the theta lying between 0 and 1 and 1 minus theta is not equal to 0 and h is not equal to 0 and h is also not equal to 0. Okay. So, we get the remainder a and then substituted this value in 1. So, put in 2, we get the result proof with the remainder term. Okay. Now, as a particular case, we can say when A is equal to 0, when A equal to 0, then the Taylor series, Taylor's expansion or Taylor's theorem reduces to reduces to the expression which is f x equal to f 0 plus x f prime 0 plus x square over factorial to f double dash 0 and so on, x to the power n minus 1 factorial n minus 1 f n minus 1 0 plus the remainder term, that is x to the power n over factorial n f n theta x, and this form is known as the Maclaurin's theorem. Maclaurin's theorem. Okay. This we get this. Now, further, if the remainder term, that is Rn which is basically equal to h to the power n or x minus a to the power n over factorial n, x to the power n over factorial n f n a plus theta x minus a plus theta x minus a. If this remainder term goes to 0 as n tends to infinity, then Taylor's theorem gives the Taylor expansion of the function f x, at the point x, at the point x or around the point 0, of course, around the point 0, at 0, Taylor expansion, at the point x minus a, at the point a, around the point a, around a in the power of x minus a. And the Maclaurin's theorem give the corresponding Maclaurin expansion of the function around the point 0. That is what you get it. Okay. So, for example, suppose I take the function f x equal to e to the power x. Write down the Maclaurin's expansion of this function, Maclaurin's expansion. So, what is our derivative? If I differentiate n times of this, is nothing but the e to the power x itself. So, this is true for every x belongs to R. So, when you take the 0, it is 1. That is, use the now Maclaurin's expansion, the Maclaurin series expansion, let it be 3. So, when you use the 3, so use 3, you will get the expansion as 1 plus x square by factorial 2 and so on, x to the power n minus 1 factorial n minus 1, and then you will get the remainder term, and the remainder term will be what? X to the power n over factorial n e to the power theta x, where the theta lying between 0 and 1. Okay. But if the remainder term goes to 0, then we get the Maclaurin series or expansion of the function e to the power x. So, here the remainder term is x to the power n over factorial n e to the power theta x. Now, if you look the e to the power theta x, now e to the power theta x, if I take this, since e to the power theta x, the value of this, if it is theta x is positive, then the value will be, that value is less than e to the power x if theta is positive. Sorry, if x is positive, because if x is positive and theta lying between 0 and 1. So, e to the power x, e to the theta x will be less than e to the power x. And when x is negative, then it is coming below. So, it is dominated by 1 always. If this, it means the e to the power theta x will always be a bounded function by e to the power x. Okay. So, it is bound, and x to the power n by factorial n, limit of this as n tends to infinity will be 0. Why it is 0? Because the reason is, when it for x is fixed, for fixed x, we can identify there exists an n such that mod of x is less than capital N. So, we can find x to the power n factorial n as x over 1, x over 2, say x over n, and then you are getting x over n plus 1 up to x over n. So, what happened? These are the finite values, and this value, so some alpha into x over, say this number, every term will be less than n. So, we can write x by n raised to the power n minus 1. So, this is less than 1 mod of this. So, this will be tending to 0 as n tends to infinity. So, this will go to 0. So, therefore, the remainder term in this will go to 0. So, expansion of h to the power x will be 1 plus x square factorial 2 plus x to the power n factorial and so on. And this will give the Maclaurin series for this. This is the Maclaurin series for the function f x, which is e to the power x. Okay. Similarly, if we take the write down the Maclaurin's expansion of the function f x equal to, say, sin x. Okay. Now, we know the derivative of the sin x, the nth derivative of sin x is comes out to is sin x plus n pi by 2, and this is true for every x belongs to R. Okay. So, take the x is 0. So, what you are getting is sin n pi by 2. Now, when it is n pi by 2, it depends on n. Okay. So, for n is even, when you are taking, this becomes pi for 2 pi etc. So, we are getting the sin x, is it not? And then the x plus theta. So, this the value of this will be 0, and for n are odd numbers, the value will be sometimes plus 1 or minus 1. So, if you use the 3, we get the expansion sin x as x minus x cube by factorial 3 plus x 5 by factorial 5 and so on like this. And what is the remainder term? R n x, the remainder term R n will be x to the power n y factorial n sin of theta x plus n pi by 2. This is the remainder. So, mod of remainder, mod of this, but this remain, and where remainder term is this, which is dominated by mod x to the power n by factorial n less than or equal to this, because this is always less than or equal to 1. So, as n tends to infinity, this will go to 0 as n. So, again we can expand it and get the series expansion for the function. So, that is what is get. Okay. So, this is all about the previous thing. Now, let us take the few problems on continuity and them. So, let us take first the problem, say exercise. So that the function, f x, which is a sin 1 by x, so that the function sin 1 by is continuous, in the interval 0 less than x less than equal to 1, a semi closed interval, but not uniformly continuous. This is our problem. Okay. So that this function is continuous, but now since this at the point 0 the function is not defined. So, we have to remove the 0 from here. Okay. So, let us see the solution. Now, for the continuity for a given epsilon r greater than 0, we are interested to find delta. So, for a given epsilon r greater than 0, there exists a delta such that mod of f x minus say any number, suppose I take alpha, mod of f x minus f alpha is less than epsilon r whenever mod of x minus alpha is less than delta. Okay. So, we can find out this where delta is alpha and del both are the point alpha and x belongs to the interval 0 to 1, is it not? So, there exists some delta, we have to identify delta. Okay. So, what is this? Consider mod f x minus f alpha. This is equal to mod sin 1 by x minus sin 1 by alpha. Now, sin c minus sin d is twice cos c plus d by 2. So, when you take the c plus d by 2, the value will come out x plus alpha over 2 x alpha into sin d minus c by 2. So, you are getting x minus alpha over 2 x alpha, this thing. Okay. Now, this entire thing cos of this is less than equal to 1, and this one is dominated by sin x, mod of sin x is less than equal to mod x. So, this is less than equal to 2 times mod x minus alpha over 2 mod x alpha, is it not? 2 gets cancelled basically. So, basically you are getting this one. Now, we have to find the delta. So, let us choose the delta as the minimum of alpha by 2 and alpha square by 2 epsilon. We will see why it is done. Okay. The reason we will come to know why we have taken this. So, when delta is equal to alpha by 2, when delta is suppose alpha by 2, okay, we are choosing delta to be say alpha by 2, then in that case then mod x minus alpha should be less than delta alpha by 2. So, this implies that x lies between 3 by 2 alpha and alpha by 2. So, when x lies between this and alpha, we are choosing taking positive of course. So, the 1 by x alpha mod of this basically is what? 1 by x is less than when you are taking. So, 2 by alpha is greater than 1 by x, it means 1 by x is less than 2 by alpha. So, this is less than 2 by alpha square. Okay. So, from here this is 1. So, from 1 if I put it this thing, then mod of f x minus f alpha is less than equal to 2 by alpha square mod x minus alpha. But mod x minus alpha I am choosing to be delta, is it not? So, if delta which is less than epsilon r, if delta is equal to alpha square by 2 into epsilon r, because as soon as delta is this is less than delta. So, replace this by this. So, alpha square by 2 get cancelled and this is less than, because mod x minus alpha I am taking delta and delta is alpha square by 2 epsilon. Okay, here. So, for this delta we get, but delta is also chosen here. So, take the minimum value of. So, that is why I have taken the delta to be minimum value of this, where both the conditions are satisfied and we get this. So, what we get, if we picked up a point x and alpha in the interval which is satisfying this condition, this is the minimum of say alpha by 2 minimum of this, then obviously this function becomes continuous. So, this shows the function f x which is sin 1 by x is continuous over the interval 0 less than 1. But it is not uniformly continuous, but it is not uniformly continuous. Why? It means uniform continuity means delta should not depend on the point. Here the delta is depending on the point alpha. So, we have to identify a delta which is independent, but we are unable to get it, that is why we say it is a. So, how this is not possible to get the delta independent of alpha. So, let us see why. Suppose I picked up the point say x as 1 by 2 over n pi and alpha to be say 2 over x is this 2 over 3 n pi. Now, both are the point belonging to the interval 0 to 1, is it not? So, pi is more than 3 and n becomes large. So, it can be less than 1 and we get. And for this, what is the sin 1 by x minus sin 1 by alpha? If I look this thing, this is equal to sin n pi by 2 minus sin 3 n pi by 2. So, when you choose the values n, the value will come out to be 2, okay? Because for n is equal to 1, the sin pi by 2 is 1, but sin 3 pi by 2, this is the function sin 0, sin 1, sin pi 3 by. So, this is 1 and this is minus 1, in fact, this is minus 1. So, when this take, we are getting adding and we get the value 2, but mod of x minus alpha, this is equal to what? 2 over n pi minus 2 over 3 n pi, 3 n pi. This will be equal to say 4 over 3 n pi. Now, n is sufficient for all positions. So, this can be made less than as small as we please for sufficiently large n, where delta is very small quantity less than 1. So, we can choose the n so large, so that but this is not true. It means this shows the function f x, which is sin 1 by x, is not uniformly continuous, because the point to point, when you take a different point, this difference is not made less than f sin r, though the point is less lying between this neighborhood. So, this shows the function is not uniformly continuous. So, this is one of the example we have. Second example, let us take, so that the function f x, which is greatest integers x plus half sin inverse 1 by x divided by x. This function, when x is not equal to 0 and the value at the point 0 is 0, has discontinuity of second kind on the right hand side, on the right of 0, on the right of 0 origin, and has discontinuity of the first kind on the left of origin. This we wanted to. It means the discontinuity of the second kind on the right means the limit of this thing, limit of this does not exist, and the left hand side, when it is discontinuity of the first kind, limit exists, but they are left hand and the limits are different. In fact, they are limits when it is of second kind, then the limit of this does not exist, while here the limit will come out to be something like infinity or plus infinity, which differs from the value at the point 0. So, let us take the solution. The function phi x, if we picked up the function say phi x, let phi x is this plus half sin inverse 1 by x. Okay. Let us take only this function, where what is the mod x? Mod x is the greatest integer function, greatest integer function. So, mod x is this, where this box x is the greatest integer function, means that is the value of this x when lies between n to n plus 1, the value of this x is equal to n, and so on. Okay. So, that is one. So, if we look the interval 0, so suppose I take the right hand side, interval, that is 0 to h. Now, in this interval, the integral here the x box will give the value 0, because all the value x which are greater than equal to 0, but less than 1, h is obviously strictly less than 1. So, in this interval the x box will give the value 0, and sine inverse of 1 by x, sorry, this is sine of inverse, yes, sine inverse 1 by x, not sine inverse, that is simply sine x. I am sorry, this is problem which I have taken is sine of 1 by x, yes, it is sine 1 by x only, not then take it sine inverse, it is just only 1 by x, okay, 1 by x only. So, it is 1 by x. Now, when you take the sine 1 by x, then this function does not have a limit at x tends to 0 from positive side, because it fluctuates. So, from it will fluctuate, it will oscillate in between minus half to plus half, if it is half function, minus half to plus half. Okay. So, the function f x, which is phi x over x, will oscillate between minus infinity to plus infinity. It means the limit will not exist. So, f is discontinuity of second kind, okay, when the limit does not exist at all, minus infinity to plus. While on the left hand side, what happened? The left hand side, if I take minus h 0, suppose I take this interval, then here x, this becomes minus 1. Okay. So, the phi function will oscillate in between minus half to minus 3 by 2. Therefore, f x, which is equal to phi x by x, will oscillate from minus infinity as x tends to 0, is it not? Because x tends to 0, it will go to minus to plus infinity, because x is also negative when x tends to 0 from negative side. So, it will go to plus infinity. So, here in this case, the here limit of the function f x when x tends to 0 exists and equal to infinity. So, it is a discontinuity which differs from the value at the point 0. So, it is a discontinuity of first kind. Okay. So, that is what is. Now, let us take a few more examples on the say I ask this question, discuss the continuity of the function f x, which is limit as n tends to infinity log of 2 plus x minus x to the power 2 n sin x divided by 1 plus x to the power 2 n in the interval 0 less than equal to x less than equal to pi by 2. Okay. Discuss the continuity of the function at the point x equal to 1. Okay. Now, let us take the limit of this function f x when x tends to 1 minus. What happens? This is the same as limit of the function 1 minus h when s tends to 0. So, this is the same as limit s tends to 0, function means limit as n tends to infinity log of 2 plus 1 minus h minus 1 minus h to the power 2 n sin 1 minus h divided by 1 plus 1 minus h power 2 n. Okay. Now, you look, when n tends to infinity, the 1 minus h to the power 2 n as n tends to infinity will go to 1 0, because it is less than 1 and power is keeps on increasing. So, it is tending to 0. So, this part is 0, this part is 0 and this limit will come out to log 3. So, basically this limit will be log of 3. Okay. Now, when you take the limit of the function f x when x to 1 plus, then this is the same as limit s tends to 0 f of 1 plus h, which is limit s tends to 0 limit n tends to infinity log of 2 plus 1 plus h minus 1 plus h power 2n into sin 1 plus h divided by 1 plus h power 2n. So, if we look that limit, now you see when h n tends to infinity, then what happens to this? This part goes to 0. So, this is the limit, since limit of this as n tends to infinity log of 3 plus h divided by 1 plus h power 2n. This will be 0, because this part is greater than 1. So, it will go to 0. So, this part is go, and what is the limit of this? 1 plus h 2n over 1 plus h 2n when n tends to infinity is 1, because if I divide by this 1 plus h, then basically this comes out to 1. So, this limit is 1 and when n is tending, so it is basically the limit of this. So, limit of f x when x tends to 1 plus is nothing but the minus sin 1. So, limit does not exist, left hand limit and the right hand limit comes out to be different. So, f is not continuous at x equal to 1, and in fact, the functional value at the point 1, if you take f of 1, the f of 1 comes out to be what? Half log 3 minus sin 1. So, that is also differs from here. So, okay. So, that part is good. Then let us come to some problems on the differentiability, or let us see. Suppose I take the function f x, if phi x equal to say f x plus f 1 minus x, and the second derivative of the function phi prime is negative in the interval 0 less than x less than equal to x less than equal to 1, then so that phi is an increasing function, phi increases of phi x increases in the interval 0 less than equal to x less than equal to half and decreases in the interval half less than equal to x less than equal to 1. Hence, attains maximum at x equal to half. Okay. Let me see this. What is given is, let function f is well defined function over the interval 0 and 1 and second derivative is negative. So, function is giving to be function f is continuous, differentiable and the second derivative exists, which is less negative in the interval 0 less than x less than equal to 1. So, this much information is known. Now, let us consider the phi dash x. Phi dash x, if we take the phi dash, this is the f prime x and the derivative of this is f prime 1 minus x and derivative of minus x is minus 1. But we cannot get any information whether f prime is greater than this or not. Okay. So, go for the another one, phi double dash x. So, phi double dash x comes out to be f double dash x and this comes out to plus f 1 double dash minus. Now, from here we claim that phi double dash x is negative for x negative why it is negative? For x belonging to the interval, say yes. Now, here we say here this is okay, y f double dash x is negative in the interval this when x varies from 0 to 1. So, since our f double dash x is negative for all x belonging to the interval 0 1 close interval. So, f double dash 1 minus x will also be negative. Why? Because when x is from for every x, because this is when x varies from 0 to 1, then 1 minus x will vary from 1 to 0. So, they always lies in the interval 0 1, and for all point which lies in the 0 1, the second derivative is negative. So, phi double dash is negative for all x in the interval 0 1. Okay. So, this is information we have got it. Achha, now, we can come now x varies. Okay. So, what we get is the phi dash x. So, our once so phi double dash x is negative. Therefore, phi dash x will be a decreasing function monotonically decreasing function. So, once it decreasing over the interval 0 to 1. Okay. Now, let me see what is that decreasing function. So, the value of the function at the point 0. So, what is the value of the function at the point 0? The value of the function at the point 0 is f 0 minus f prime 1. The value of the function at a point half phi dash a at the point half is nothing but what? Phi dash half, this becomes what? When you take f prime 1, this is 0, f prime half minus f prime half, which is 0, and then value of the phi dash at the point say 1. What is this? F prime 1 minus f prime 0. So, what is this? This is the function phi dash. Phi dash is this function which attains the value this is 1 interval, this is half. So, phi dash attains the value 0 at this point, and then these values at the point 0 is this value, at the point 1 this value. Now, phi dash and phi dash a, they are differing by minus sign only, because minus times of this number is the second. So, if it has a positive value here, this will have a negative value here, and if it is negative value, then this has a positive value. But phi dash is a decreasing function. So, phi dash is decreasing means it cannot go from negative to positive. So, what we get it that since it is monotonically decreasing, so we can consider from here is that in between 0 to 1 phi dash must be positive. So, here it should be positive, here it should be negative, and there, so that it decreases and cross the x axis and going down. So, this shows that the function phi dash x is negative for x belonging to the interval 0 to half, and positive for all x belonging to the half and 1. It means this implies the function phi. What is the function? Therefore, our function phi is a phi function is decreasing in the interval 0 to half and increasing. No, it's wrong. It's the other way around. Sorry, it's the other way around. This is positive. This is greater than 0 in this interval, and this is less than 0. So, this is increasing function in the interval positive. So, it is increasing. This is what it's coming. No. It's I am sorry. What is this? Is this function phi dash? If it is positive, it is increasing. Oh yes, and then it is decreasing. So function will be something like this, and then at the point half, it is coming to be at the point half. What is this is? Yes, yes, at the point half. So it is decreases, is it not? So it will go like this. So maximum value will come at the point half. Yes, so we get this. So this is our increasing in this and decreasing in the interval half to 1. So our function f phi which is this function phi, this function f x. So what we get is the phi x increase in this, decrease in this, and attains the maximum value at x equal to phi. So phi at x equal to half, it will attain its maximum value, is it not? Because then only we are getting the function phi dash is this 0 and this one is 1. So here it is f dash 0, and then f dash 0 is greater than this, f dash 0 is greater than this, and this is negative. That is why it is coming. So it is coming to be just like that. Okay. So we get this one, the value at the point this is basically at the point x equal to half, this function is this. So what we get is that increases in the interval. So function phi is increasing in the interval this, phi dash x is greater than 0 and this is less than 0. Okay. So we get this one and the phi dash x. Okay. So this shows our result is okay. So that complete the result. Right, something is wrong.